Hello, so I'm Felix, and I'm going to make a short presentation about our recent work on embodied language learning at DeepMind. So the goal of grounded language at DeepMind is to work towards models that exhibit convincing embodied understanding of language as it pertains to the external world. Ultimately, we would like to develop learning systems that can do the sort of things you see in this image. So interpret instructions given by human users and respond, both by carrying out the necessary movements to get things done, but also by producing useful language responses. Now, one way of going about this problem is to break it into separate subproblems. For instance, language processing, motor control, or vision. Of course, doing this has led to an enormous amount of impressive breakthroughs in recent years. So the development of ideas and techniques, including large-scale language modeling, powerful algorithms for learning motor control, and also flexible algorithms for learning large-scale image representations and image recognition. Now, while we intend to lean greatly on those advances, the approach we take in this work is a little different. And it's beautifully motivated by a paper that has been very influential to me. It's called More is Different, and it's by P.W. Anderson, who wrote it in 1972. So he's a theoretical physicist, and he argued that we may never entirely understand or explain complex phenomena by explaining each of the subparts in isolation, however precisely you explain those subparts. So one reason to agree with Anderson on this one is because he was a Nobel Prize winner. But another reason is some empirical observations that we've been uncovering in our recent work. To see this, consider a visual question answering task like the one shown here. So we have a very simple language model to encode language into a distributed representation, and we have a CNN visual encoder. And the input from those two concatenated together must provide the basis for answering questions about still images like you see here. And the only possible answers are on the left side or on the right side. So there's only two possible predictions this model can make. Now, we're interested in how well this model learns to generalize in a compositional way. So to measure that, we construct a training set in which some of the possible colors and shapes form part of the training questions that the model gets. But we importantly hold out a few of the different color shape combinations to measure the performance of the model on those testing combinations. And when we do this, we see that we can train this untuned baseline model to 97% accuracy on the training set, but it scores 78% accuracy on these held out combinations in the test set. Now let's compare this model to an entirely embodied agent, to which we can give a problem which is essentially the same. So rather than giving this agent a question, we give it instructions, but the agent has to respond by moving slowly towards the correct thing that was instructed and bumping into it. Now, structurally, this is exactly the same as the scenario we gave the visual question answering agent. So again, we can train it on episodes which use the exact same subspace of color shape combinations and test it on the exact same held out set. And importantly, in both the case of the visual question answering model and the embodied question answering agent, we keep the architecture essentially the same. So the only small difference is in the final layer, where the embodied agent has to choose one of 8 possible actions at every time step, whereas the visual question answering model sees that first frame of the episode and just has to make a single prediction of either left or right. When we do this and compare the performance of the agent on the one hand with the visual question answering model on the other, we notice 2 interesting things. So firstly, it's kind of interesting that the agent actually learns the task in many fewer frames. This isn't fewer episodes, this is actually fewer amount of raw frames going into the agent. So this is probably because it can really move up, get a different views of the object from different angles and bump into them at very close range, building up its ability to discern the important distinctions between the objects. However, it's important to remember that both of these models eventually end up scoring similarly on the training set, close to 100%. So perhaps the most interesting difference between the two conditions is performance on the test set, where the visual question answering model gets 78% accuracy, but the embodied agent actually gets 100% accuracy, just the same as on the training set. So one way of explaining this is just to say, well, the embodied agent just gets better representations, whatever that means. It gets a much richer stream of experience seeing these objects from a range of different viewpoints, and that contributes to its representations improving, which allows it to generalize better. And that's certainly a very plausible explanation. But another thing to remember in the scenario of the embodied agent is just how uncertainty might manifest itself in such a model. So in order to get a test prediction wrong, the embodied agent needs to get many different action decisions wrong as the agent unrolls in a particular episode. Now, if there is some uncertainty in the model, the probability of getting all of those wrong, such that the agent actually bumps into the wrong object and fails to score well on a test episode, is perhaps very, very low. Whereas all that the VQA model needs to do is make one single incorrect prediction. So I think that's a very interesting thought experiment and way to consider that if we study certain problems in an embodied agent, we may actually find quite different outcomes from if we study them just in this non-interactive scenario of an individual model. But it's not just the distinction between interacting or being embodied on the one hand and being a static model on the other. Even in the scenario where two agents have some degree of embodiment, the nature of the environment can contribute to quite a large degree to the actual outcomes of experiments that we might run. So to consider this, we did experiments in two different environments where we were essentially able to run the same overall high-level experiment. So in one case, it was a 3D room environment built in the Unity game engine. And in the other case, it was this much more prosaic-looking 2D grid world. But importantly, in both cases, we were able to put exactly the same things. So you can see in the Unity world on the right, there is three smaller movable objects and one large piece of furniture in every episode. And importantly, all of these things begin life at random locations at the start of every episode, as does the agent. Then on the right-hand side, we create exactly the same thing, right? So those red shapes that you see there are the movable objects. The white square is the agent, and then there's a white other shaped thing, which is a piece of furniture. And again, at the start of every episode, all of the locations of each of those things are randomized. Now, in this environment, we can construct a task which we can run in both of the two settings that I just described. So it's another test of combinatorial generalization. In this case, we're going to train the agent to lift all of the possible objects in the global set that the environment contains. And in both cases, there was the same number of possible objects that the agent could interact with when lifting. And then, importantly, we're only going to train the agent to put some of the objects in a particular location on the piece of furniture. So the agent gets trained to know what all of the objects are. It learns the name for all of the objects when it learns to lift them, but it's only had experience of actually doing something useful with a subset of those objects. And we can run exactly the same training regime in both environments. And we can execute exactly the same testing samples in both environments. So when we test these agents, the challenge we're getting it to do is to see if it can actually put an object in the useful place when it's never been trained to put that object in the appropriate place previously. It's only been trained to walk up to that object and lift it. Now, on the left-hand side, we see that when we train the agent to do this, it actually does pretty well on the test set. So here's a video of the agent actually picking up and putting objects on a bed that it was never trained to put on the bed. It was trained to put other objects on the bed, but not these specific ones. Now, if I run the video on the right-hand side, you can see the agent doing the equivalent test samples in the 2D grid world. There's a bit of uncertainty. In that episode, it does actually succeed. But what we observe is that there's much more uncertainty. Once the agent picks up the object, which it was trained to do, it's much more uncertain in its ability to actually take that object and move it to the correct place. And if we actually look more quantitatively at the success rate of the agents in the two regimes, we see the effect we saw of uncertainty manifesting itself in the numbers. So the blue line on this chart is the performance of the agent in the 3D world on the test set as it learns, and the orange line is the performance of the agent in the grid world. Now, we were really interested in this effect, so we dug a little bit deeper to try and understand exactly what it was about the differences in these two environments which contributed to this quite large difference in systematicity. And to investigate that, we thought about what are all the plausible, meaningful differences between the two settings. And one thing we stumbled across was this notion of egocentric perception. So to investigate this, we actually took the 2D grid world, but we gave it an egocentric flavor, much as the agent has in the 3D Unity world. And to do this, we just put a box which limited the agent's vision around the agent, which was centered on the agent and moved with it. So now this is an imperfect information scenario where the agent cannot see all of the environment from a single viewpoint. And interestingly, when we did that and otherwise ran exactly the same training test split as we'd run previously, we found that this notion of egocentric perspective, giving the 2D agent in the grid world an egocentric view of the world, actually explained the vast majority of the difference in generalization between the two conditions. So this tells us that the nature of the agent's experience and the perspective that it has can actually contribute in an interesting way to providing sort of useful inductive biases in the agent's learning mechanisms. And in turn, that can lead to differences and hopefully improvements in the ability of the agent to generalize. Note, of course, that the language that the agent's getting on these tasks, they all relate to the relationship between the agent, objects, and other objects. And perhaps it's just the fact that having that egocentric perspective where various different frames and observations in the environment come to actually look the same from that viewpoint is a useful invariance which allows the agent to learn more useful representations when it comes to interacting with the world in this egocentric way. But of course, so those experiments told us a little bit about the agents to generalize productively to instructions that contain novel combinations of familiar words. But we were also interested in developing an agent that is robust to entirely new words. And for this purpose, we leveraged the power of unsupervised learning. And in particular, we investigated whether we could embed instructions into the rich representation spaces acquired by large predictive models like BERT. So with a pre-trained BERT model installed as the language encoder in this agent, we can train it as before on manipulation tasks in the Unity environment to follow synthetic template instructions generated by that environment. Now, importantly, we don't backpropagate into the BERT weights in this agent because a lot of training is required to learn the RL task, and we think that would degrade the quality of the BERT representation such that it wasn't able to generalize in an interesting way. However, as the agent learns, the remaining weights that are updated in the agent do come to adapt to the BERT representation space. And to evaluate the agent, once we trained it in this way, we got test instructions not from the environment, but instead from actual real humans. There are, of course, a lot of interesting architectural choices to be made when considering integrating a BERT model into an agent in this way, particularly because BERT returns not a single sentence vector for each instruction, but rather a list of contextualized word piece representations. So, of course, one way of integrating that list of word representations is to pull them into a single vector and concatenate that with the vision module. But an alternative way is to train a further cross-modal self-attention layer. As the agent learns, it's trained in the environment to adapt the representations in the BERT representation space in a way that is optimal for the agent to use in order to follow instructions. Another thing that we found very useful in this agent was the addition of typo noise during training. So we can put a little model on the language generator in the environment so that while it's generating templated language, it does come to have some of the natural typos and mistakes that that might come as the output of a speech recognition system or might be produced if a human user was typing instructions for some agent in this way. Finally, we had what I think was an interesting way of gathering realistic instructions from human users to be able to train our agents. So to achieve this, we put humans into the game environment rather than just getting them to paraphrase the template instructions. And the advantage of this was that we got access to the full sort of level of ambiguity that a human might come up with while they were instructing a robot in reality. So in this case, we put them into the room, as you can see here, and we asked them to imagine asking another robot or agent to lift up one of the red objects and put it on one of the white objects. So we didn't prime them for the object names, and the humans had to come up with whatever they thought was a reasonable way of referring to each of these objects. As you can see, this led to quite an array of interesting and challenging test examples for the agent to get to grips with. So in this case, for example, the agent, the human instructor referred to that thing there as a mosquito bat rather than a tennis racket. And here, the instructor thinks that this thing is a toy fan, whereas in actual fact, it's a helicopter. And then a later instructor referred to it as an helicopter, which shows you that not all of our raters had strong written English, but of course that's a realistic scenario that we'd like our agent to be robust to. So just to go over the results, we found that the agent with BERT embeddings and the full cross-modal self-attention was the agent that performed best, and that adding typo noise to the training loop actually made a very large difference in the robustness of the agent to cope with human scores. One notable thing is that doing this typo noise with full contextualized BERT embeddings yields much better performance than doing so with the more conventional word embeddings that we might find in the first layer of the BERT model. So this tells us that it really is the powerful contextual sentence encoders in BERT that are actually making a difference, despite this domain being quite constrained with respect to the type of language that humans are giving. Another point of comparison is that humans themselves aren't actually that much better than our best trained model on these tasks. So when we gave the human instructions to different humans and had them play the task using the keyboard, their success rate was similar to that of our best agent. That tells us that there is, a high degree of ambiguity in these instructions, and it's perhaps not realistic to expect an agent to ever get something like 100% in these tasks. So anyway, just to give a bit more context, here's a video of the best agent successfully and sometimes unsuccessfully following human instructions. So at the top is the instruction the agent was given from the human rater. So in this case, it's asked to put the Casio in the box. It fails at that one. It didn't know that Casio is equivalent to a keyboard. In this case, it's asked to put a tractor into the bed. The instruction it was trained on was put the train on the bed, and eventually it gets there. So it's probably the case that there's quite a lot of uncertainty in the agent, but of all the objects that it could find in the room, the train was the one that was closest to the tractor, and therefore eventually it did get the right thing. So applying BERT to an agent in this way is a really nice indication of the power of representation learning and how it can actually feed into the knowledge integrated in an embodied agent to exhibit grounded language understanding. And one of the key insights from the BERT model, I think, is a very old one, which is the power of prediction and how valuable it is for learning representations. This is actually a really old idea, so it goes all the way back to Helmholtz's early work on perception. In the 80s, McClelland and Rumelhart proposed a model for understanding the perception of letters in the words. And then Jeff Ellman made a very influential model of recurrent network, which was able to induce semantic and syntactic structure just by predicting the next word in some text. And then finally, the idea of predictive coding has then become very influential in neuroscience. as described in works like that of Rao and Ballard in the late 90s. And more recently, in deep reinforcement learning, the idea of prediction as a way of building up the knowledge inside agents has become more and more popular and exhibited more and more strong results. So there's a bit of a DeepMind bias in the examples I've chosen here. And there are, of course, loads of other studies that have shown similar things. But each of these studies tells us that by predictive auxiliary learning, so we could think of it as unsupervised or semi-supervised learning in an agent that's otherwise trained by reinforcement learning, we can increment and build up the internal knowledge in the agent such that it ultimately is more able to do the things that we would like it to do. So given that there are now various competing approaches to improving the latent knowledge acquired by agents, in some recent work led by an intern in the group, Abhishek Das, we investigated the use of embodied question answering as a means of quantifying the general or even propositional knowledge acquired by agents as they explore their environment in an otherwise task-neutral way. So to do this, we coded up an environment in the Unity room as before, but to generate episodes with different arrangements of objects and also to produce template-based questions that make sense and have a reasonable distribution of possible answers given the objects that are instantiated in the current scene. So the set of questions can be broken into different categories, including those could be answered from a single frame, like what color is the cup, those that refer to the relationships between objects, like what is the color of the mug near the table, and those that require the agent to explore and remember details about its entire surroundings, like how many balls are there in the whole room. Importantly, because we're interested in EQA as a means to quantify and evaluate the BERT-style knowledge, which we can aggregate into our agents using these unsupervised predictive objectives, we didn't train the agent directly to answer the questions returned by the environment for each episode. Instead, we trained agents with different knowledge-building predictive losses simply to optimize a question-agnostic objective to visit as many objects in the room as possible in a given time frame. Now, as the agent learns this policy, the knowledge-building predictive algorithms, in theory, endow it with the general information it needs about the world it inhabits. Then, to probe this knowledge in the agent, we simultaneously train a question-answering decoder whose inputs were the particular question provided for the environment for that particular episode, together with the current memory state of the agent's activations at a particular time step. So again, just to reiterate, we don't backpropagate from the question answer into the state of the agent. We're interested in to what extent its memory state can provide the information together with a question that allows the question answering decoder to answer these questions. Now, here are some results for the model averaged over all the questions in the training set. And just for comparison, we had two controls. So the blind control is an agent with no visual input, and this is used to measure biases in the questions themselves. The oracle control is an agent whose representations are explicitly trained to answer the questions. So we obtain this by removing the stop gradient, which comes from the QA decoder and goes back into the memory state of the agent. And to compare with this, we consider three different types of learning agent. So one of them is what we call the model-free agent. This is just a baseline Impala agent. Then we consider an agent which is endowed with an algorithm called action conditional CPC. This is a loss where, conditioned on the current memory of the agent, a predicted head is rolled forward and must choose, based on the actions that the agent actually took at individual time steps, whether or not an observed frame in the future is a real observed frame from the trajectory that the agent actually acted in, or whether it's a dummy negative example of a frame taken from somewhere else in a different trajectory. And to compare to that, we also evaluate an agent with a SimCore loss, which is an unrolled overshoot objective where the agent must recreate the pixels, estimate the probability of the pixels in the observations, a sort of randomly chosen number of time steps into the future at a given episode. And looking at the results here, we can see that the agent with the sim core objective actually seems to build up much richer representations than the agents with the other predictive objectives, allowing the question answering decoder to answer questions about the environment conditioned only on the memory state of this agent at about the same accuracy as an agent which was trained end-to-end to answer the questions. So here's a video of the agent with the sim core and the output of the question answering decoder conditioned on its memory state. So you can see that in this episode, it's asked a question, what is the aquamarine object? The correct answer is grinder, as in like a salt and pepper grinder. And as the episode goes on and the agent explores its environment, the agent's confidence, or the question answering decoder's confidence in the correct answer actually grows. And here's the equivalent visualization for the question, how many blue objects are there? So here the agent really needs to look around and count all of the objects, be sure that the answer is 1. And in this case, the confidence again increases until by the end of the episode, it's relatively certain that there's only 1 blue object in the room. And here we can see the results across all of the different question types. One interesting takeaway here is that, of course, each of these different types of questions is really quite different in difficulty in terms of how easy it is for the agent to retain the necessary information in its memory in order to be able to answer these questions for different categories. But one important takeaway is that this sim core loss, the objective of predicting what state the environment will be in at a large number of frames in the future, and actually doing that, computing that loss at the pixel level, seems to lead to the richest degree of general knowledge accumulating in the state of the agent, particularly if we're interested in question answering style knowledge that enables an agent to answer this sort of these questions about propositional facts about the environment. We also ran an equivalent experiment to the holdout experiments that I referred to at the start of this talk. And we find that there's a degree of compositionality in the way that the agent expresses and represents its knowledge in its memory state. So we can actually do a holdout test and observe that the question answering decoder is actually able to answer questions that it itself was never trained to answer, provided they're comprised of familiar individual components. So that's sort of evidence of a degree of compositionality in the representational state of the memory of the agent, and also in the way in which the decoder is trained to extract that information. So just to summarize the whole talk, I've described how our goal is an embodied agent that exhibits a credible understanding of language by both following instructions and answering questions. And I've also described how learning to use language may become more, not less, achievable as the environment that agents get to learn in become richer. So we often have this principle that more is different, which we took from Anderson's famous paper in 1972. Of course, by using things like unsupervised learning algorithms on raw text, an agent that's trained on synthetic template language can actually be made much more robust to real human instructions. And I've also shown how agents can acquire some of the knowledge necessary to answer general knowledge questions about their surroundings, but their ability to do that is much greater if they're given powerful sort of semi-supervised or unsupervised predictive objectives, as well as optimizing an RL objective or a task-based objective. So thanks to a load of amazing collaborators who've all contributed immensely to this work. I'll finish up with a little video of the agent having fun putting aeroplanes on beds, and thank you very much for your time.